All right, so let's talk about topic 46, concavity and points of inflection. Now you're going to see a lot of similarities from what we did yesterday, but let's see even what concave up and concave down means. So I'm going to put some points along this curve, and I'd like both these curves, and I'd like for you to draw in just the tangent lines at those points. So stop the video and draw those tangent lines. And when you do that, hopefully you drew something like this. So notice that when you have a graph that is concave up, and that's what this one is concave up, notice that the tangent lines fall below the graph of f. Versus a concave down, okay, this one was concave up, a concave down piece, the tangent lines of f lie above the graph of f. Now that's going to come back in play because a while back we talked about linear approximation, and we were proving whether a linear approximation was an overestimate or an underestimate, and I said, later on I'm going to give you a more solid way of doing that. And it comes down to concavity. Because if the tangent line is above, then the tangent line approximation is going to be an overestimate. If the tangent line falls below, then the tangent line approximation is an underestimate. So it's going to come down to proving concavity, and that's what we're going to look at, how we're going to do that. So f is concave up if f prime is doing what? Well, here's a concave up piece, and think about these lines. Notice the derivative, if I put a slope to these, they're all positive, but what's going on? This one's close to 0. It's getting steeper and steeper, so f prime would be increasing, and the same relationships are true between f and f prime and f double prime. So if we have a function that is increasing, then its derivative is going to be, okay, positive. Okay, so if I do the same thing with the concave down, these are also positive, but that's like 10. This is like 3. This is getting smaller, so it's closer to 0, like 1/2. So those f primes are decreasing, or in other words, f double prime is going to be negative. So we're going to use the second derivative. Most of the time we're going to use the second derivative to go back to concavity. So we're just giving you a lot of different thoughts here, and then we'll actually do a problem. So a point of inflection, which I will abbreviate as a POI, then writing point of inflection, is a point where f changes from concave up to concave down or vice versa. In other words, where f is changing its concavity. So notice right here, this piece is a concave down piece. Okay, concave down looks like a frown. And then this is a concave up piece. So this point where it changes is called a point of inflection. So possible points of inflection, again, underline possible, that's when the second derivative either equals 0 or the second derivative is undefined. Okay, but just like with maxes and mins, just because the second derivative equals 0 to place doesn't mean necessarily that it's a point of inflection. F double prime must change sign. And let me point out again, f must be defined at that point. And what I mean by that, let me show you an example of the be defined part. If I drew a graph like this, I just did a standard like 1 over x. This piece right here is concave down. This piece is concave up. So I could say that at x equals 0, if I did a sign analysis at x equals 0 of the derivative, this would be negative and this would be positive. The second derivative would be negative here and positive here. However, so f double prime does change sign, but the function isn't defined at 0. What's happening is I have an asymptote. So there can't be a point of inflection when there isn't a point. So that's the f must be defined part. So it does change concavity, but in this particular graph, you would say there is no point of inflection because, again, where it changes concavity, there isn't a point. So you have to check for that as well. So let's do an example and kind of put this all together. It says find all f prime and f double prime information for that polynomial. Now, I want you to stop the video and I want you to see if you can do the f prime information, because that should be a review of yesterday, so it's good to see if you really can do it all on your own. So stop the video and try and come back. So here we go. F prime, what do we have for f prime of x? F prime of x would be 4x cubed minus 12x squared. And I'm going to go ahead and do a factoring step. 4x squared, and that would be x minus 3. So I can kind of tell that by looking. I'll just go ahead and put equals 0. I'll set it equal to 0 and say that f prime equals 0 when x equals 0 and x equals 3. So that means if I do a sign analysis on f prime, I'm going to put 0 and 3. Now I'm going to be smart about this. That part's always going to be positive, right, since x squared. So it really comes by this factor, x minus 3. So a number bigger than 3 is going to be positive, less than 3 is going to be negative. So I kind of visualize f. It's going to decrease, decrease, and then increase. So what information could I say? Again, depending on which order you'd like to write it in. F has a local min at x equals 3. Now it does say to justify all answers, since f prime changes negative to positive. And what else? We also know from the first derivative, f is increasing. And remember, I'll write this one first when f prime is positive. Therefore, 3 to infinity. Notice on that one I wrote the justification first. Again, either way is fine. F decreasing when f prime is negative. Therefore, now, can I write those together? What did we say? We said if I have a repeat of sign, the good news is polynomials you can always combine because they're going to be defined everywhere. So f of 0 does exist, so they would want you to write that as an interval like that, negative infinity to 3. Don't forget as well, if they ask for the specific point, if I wanted to do a local min of a certain value, remember, I could find f of 3. What is that? 3 to the 4th is 81. 81 minus 4 times 27. A little mental math there. Well, 81 is 4 times 24. That'd be negative 27. Had to just think for a second. So this local min, of course, if they ask you for the point, then you could say that the point was 3. On the graph, you're going to have a point at 3, negative 27. All right? Okay, so that's the first derivative. Now, here's the new part. I'm going to go through that same process, but I'm going to find the second derivative. Now, it's easier on the second derivative. I'm certainly going to look here and not have to do the product rule. I would get 12x squared minus 24x. Once again, I'm going to factor And notice, I'll write this one this way, that the second derivative is equal to 0 when x equals 0 and 2. Never going to be undefined, because again, with polynomials, your derivatives are never going to be undefined. Now let me do a sign analysis on that. With those numbers. So here are my possible points of inflection. Again, just because I get them here doesn't mean they're points of inflection. I have to do a sign analysis. And a sign analysis, I can plug in, or I can realize a positive x squared with 2 zeros is always going to go plus minus plus. Which means what? That yes, when the second derivative is positive, you're going to have a piece that is concave up. It's going to go concave down and concave up. This is f. Remember, we're talking about things on f. So here are my answers. F is concave up when f double prime is positive. So since that's true, where's that going to be? That's going to be at negative infinity to 0 and 2 to infinity. F is concave down when f double prime is negative. So that's going to be from 0 to 2. Now, do I have a POI? Well, my second derivative certainly changed sign twice. And again, since I know my function is always defined, I in fact have 2 POIs. So f has a POI, I'm going to write this one this way, at x equals 0 and 2 since f double prime changes sign. And once again, if I'm going to plot this eventually, which that's the whole point of curve sketching, is eventually to get a curve, I most certainly could get the ordered pairs of these points if needed. But remember, when I get the ordered pairs of the points, where do I plug in? Do I plug in here? No. You're finding points on F. Well, 0 is easy. If I plug in 0, I get 0. If I plug in 2, what is that? 16 minus 4 times 8, so minus 32, so that's negative 16. I can get those y values by plugging into the original function. So that's how you use the second, when it says find all f double prime information, that's what you are finding. Okay? Now looking at example 2, I want to be very clear. This question says find the point, or points, I guess it should say, you don't know how many it's going to have, point or points of inflection for that function. Well, when this question is asking you just for the points of inflection, you think, well, I got to get the second derivative and see where the second derivative changes sign. Okay, does it change sign at a particular point? Well, if I have to find the second derivative, then I have to find the first derivative. So I'm going to go and do that, which of course I'm going to do by ho d high minus high d ho over ho ho. Now if I clean that up, you might could do that in your head. That'd be negative x, so those x's would cancel. 2 minus a negative 3, that's actually 5 over x plus 2 squared. And being that I'm about to find the second derivative, I'm even going to write that like this, because it's going to be a lot faster for me. Because if I write the first derivative like that, my second derivative, instead of doing the quotient rule, I'm going to do the power rule. Power to the front, negative 10, decrease the power by 1, which is negative 3, multiply by the inner derivative, because I always have to remember chain rule, which would be 1. Now I'm going to write that like this, negative 10 over x plus 2 cubed. So what can I see from that? I can see that f double prime is never equal to 0 because that numerator will never be 0. However, f double prime is undefined at x equals -2 because that would make the bottom 0. Well, with my sign analysis, again, I put in -2. Let's look. The top is always negative. If I put in a number like 0, my bottom would be positive. So overall, that's going to be negative. But if I put in a number like -3, the denominator will also be negative. So a negative divided by a negative is positive. Okay, so I have a POI at -2 because my derivative changed sign. Oh, what terrible, sort of terrible thinking. Yes, I love the fact that you say, oh, the second derivative is changing sign, so you have a point of inflection, but you've got to look at the original. If you actually tried to find the point, when you plug in f of -2, you get -5 over 0. This is undefined. What's going on at -2? You have an asymptote. So there are no POIs. Okay, you do have a concave up piece and a concave down piece, but there are no POIs. So there you go. You can be working on your homework and going from there. All right. I will say that in the homework, being that we wrote it in the notes, you don't have to justify. It doesn't ask you to justify your answers every time because that would take you a lot of time writing. We did write it out good in the notes, so if you're asked to do that on the test, you will have that. But you don't need to write that in the homework because it will take a long time. All right. See ya. Peace out.